Hello and welcome to the first mobile graphics meetup. My name is Dihara and I'm a developer technology engineer at Imagination. So today we'll be talking about the Unity high definition render pipeline, and we'll be looking at some of the rendering techniques to help you get familiar with the internals before it's available on mobile. So we will start off with a recap of the existing pipeline in Unity. Then we'll talk about the scriptable render pipelines, and then we'll get to our main topic, the HD pipeline. We'll look at some of the interesting techniques and optimization for this. And finally, we'll finish off by comparing it to the universal render pipeline. So let's get started. So the built-in pipeline gives you a choice between a deferred and forward rendering path. And it also has support for compute shaders and custom shaders written in HLSL. It also supports command buffers, which is a common feature in modern graphics APIs. And post-processing is mainly handled via the post-processing stack that's available freely from the Unity Asset Store. However, it does have its share of problems. So mainly it's a black box system, meaning that you can't really change the internal rendering logic. You can only change a few options through the configuration. And the one-size-fits-all approach means that you cannot really utilize the strengths of the platform you're working on, such as tile-based rendering on mobile and asynchronous compute on desktop and consoles. And performance has some room for improvement too. So the solution for this was scriptable render pipelines. So this is a new API for creating pipelines introduced in 2017. So in this pipeline, performance critical components such as culling, sorting, and batching are all handled in the C++ side, while you write your high-level rendering logic such as camera setup and various rendering techniques in C#. Out of the box, we have two pipelines, the HD pipeline and the universal render pipeline, also known as the lightweight render pipeline previously. So let's start off by looking at the HD pipeline. So the HDRP is a high-end render pipeline that uses many cutting-edge real-time rendering techniques. It's currently available on desktop and consoles, and it also supports modern rendering APIs such as Vulkan, DX12, and Metal. It is said to be available on Android and iOS in the future as well. So for this presentation, we'll be taking a select few of the rendering techniques in this pipeline and diving deep into them. So these are light culling, physically based rendering, volumetric lighting, screen space deferred decals, and post-processing. So let's start with light culling. So Unity uses tiled and clustered light culling for building its light lists. And in case you don't know, tiles are a grid of 2D squares that form the screen. These form smaller frustums that you can cull your lights against, whereas in clustered shading, you have these tiles which are also split along the z-axis, forming a volume of these smaller frustums. In tiled rendering, this is used for opaque objects in Unity, while clustered is used with transparent objects. So let's look a little deeper at the actual culling algorithms used. So Unity is taking a hierarchical approach to culling. Now, before starting, lights are frustum culled on the CPU side. And once they are passed over to the GPU, they are first run through a compute shader that computes screen space AABBs for these lights. So here you can see a spotlight, a point light, and a secondary spotlight, and we are computing the AABBs for these lights. So next is a coarse intersection test between the 2D AABBs and tiles sized 64 by 64 pixels. Now, after this test, there's a narrow intersection test done to build the resulting tiles and clusters. So this technique is completely performed on asynchronous compute in parallel to shadow map rendering to reduce the overhead. The actual tiled culling is based on the fine-pruned tiled lighting technique. This operates on 16 by 16 pixel sized tiles, and this diagram here shows a 4 by 4 pixel portion of this 16 by 16 pixel tile for convenience. So they first start off by finding the min-max depth for this tile, and then they will call the lights from the coarse intersection pass against the tile bounds, and they are stored in local data storage. So here we see a spotlight and a point light. These are culled. And the next pass is fine pruning. Here they loop over the resulting lights on each thread and test 4 pixels to see if they're within the shape of the light. If none of the pixels are within the light's shape, they're not added to the list. So this is followed by the clustered culling pass. So unlike tiled, this pass operates on 32 by 32 pixel sized tiles, and it simply tests the resulting lights against the cluster bounds and assigns them to their respective cluster light lists. So this is a basic look at how Unity achieves many light shading in this pipeline. So now we can move on to our next topic, which is physically based rendering. So we'll start off with standard materials. So for diffuse, Unity is using the Burley diffuse term, also known as the Disney diffuse term. Although very similar to Lambert, there are some differences in reflections at grazing angles. Now, the actual BRDF is simply the Lambert term with 2 added Fresnel terms, as you may see here. For specular, they are using the multi-scattering isotropic GGX term, and specifically they are using the Smith GGX visibility term. Now, from these images seen here, you can see that as the roughness increases, the surface becomes less brighter with single scattering. However, in multi-scattering, consistent brightness is maintained throughout the roughness levels. Now here you can see the G-buffer format that's used for standard materials. Now this is also a great candidate for using pixel local storage or subpasses in Vulkan for use in the mobile port. So iridescent materials are based on the paper A Practical Extension to Microsurface Theory for Modeling of Varying Iridescence. Now, this paper describes a method for applying a thin film layer on top of dielectric materials to simulate iridescence. Although the paper uses spectral integrals, this is simplified for real-time use as a RGB triplet phase shift. So this resulting thin film layer reflectance value is used to replace our Fresnel value, giving us this final iridescence output. For anisotropic materials, they use the anisotropic version of the Smith GGX visibility term used in specular. Now, this technique is based on the optimizations done in Far Cry 4, and this implementation requires a per pixel tangent frame. So let's see how they've packed this tangent frame into the G-buffer. So to save space, what they've done is they've saved the angle between the normal mapped tangent frame and the default tangent frame, which is from the interpolated vertex normals. And this is stored in the G-buffer. And during shading, they reconstruct this tangent frame from this stored angle. Now let's move on to subsurface scattering materials. So subsurface scattering is a mechanism of light transport, where light enters the surface of an object, scatters internally, and exits at a different point. Now, the subsurface scattered contribution at any given point is generally computed using a bidirectional subsurface scattering distribution function, or BSSDF for short. Now, here's what it looks like as a formula. Now, that's a pretty nasty integral. However, if you look at the inner integral, you'll notice that it's integrating over a hemisphere similar to our rendering equation, and the outer integral is over the surface area of the object. So ideally, we'd have to calculate the incoming irradiance at every single point in order to determine the amount of scattered light exiting the surface. Since this is too expensive, this formula is simplified as follows. Now, it uses the distance between the exit point and the current sample as an input to an attenuation function called a diffusion profile, which can be visualized like this. Now, since we still cannot afford to integrate over the entire surface, we use Monte Carlo integration to approximate this integral with a smaller number of samples. So the implementation in Unity starts with pre-computing sample positions, which are used for disk sampling this diffusion profile. So next, during the lighting pass, the incident radiance is computed and written to a render target, which in the next pass we use to sample the radiance around the current point. Now, this is done by using the previously pre-computed sample positions. However, these points have to be projected onto the surface of this object. Now, to help with this, what they do is they conceptually place a disk of samples on the surface centered around the current shading point. Now they can sample the diffusion profile and calculate the scattered light. However, this could result in color bleeding because in certain cases, these projected sample positions could belong to the background. Now, to solve this, they use bilateral filtering for the convolution, which takes depth into account. So the disk used for this projection is oriented to face the camera. However, this is not optimal as the distance between the sample positions changes depending on the angle. Now let's look at how this subsurface scattering technique is integrated into the pipeline. Now, during the depth pre-pass, materials with subsurface scattering are masked out with the stencil buffer. And in the deferred shading pass, the subsurface scattered materials and standard materials are shaded separately and then composited together. Now, in terms of optimizations, this entire technique is implemented in compute shaders. So because of this, they have heavily optimized it to use local data storage. And in this image here, you can see this highlighted region is the global work group. And this area is the local work group. And this larger area is the local data storage cache. Now, each thread loads in a radiance and linear depth value into the cache at the beginning. You can also notice a 2-pixel wide border around the cache, and this is there to increase the number of cache hits. Finally, this circle is the sampling radius for our diffusion profile. And as you may notice, a majority of the samples lands within the cache, thus reducing the number of redundant texture fetches required for subsurface scattering. Now, another part of the subsurface scattering pipeline is translucency. So this is handled via 2 approaches in Unity. One is for thin objects and the other for general purpose objects. So for thin objects, they used the simple subsurface scattering model from the mentioned paper here. And a couple of assumptions are made here, mainly that the back face normal is the reverse of the front face normal, and that the object has constant thickness, which is taken from a texture. And because the object is thin, they assume shadowing is the same for both faces, thus allowing them to use a single shadow map sample. Now, these simplifications make it possible to analytically integrate the diffusion profile over the back face. For thick objects, however, they estimate the thickness using the shadow map. This is done by taking the difference between the depth of the current pixel in light space and the closest depth in the shadow map. The minimum depth is determined by the thickness texture. So hopefully this section would have given you a better understanding of the material systems used in this pipeline. Now let us move on to our next topic, which is related to PBR, and it is volumetric lighting. So the implementation used in Unity is based on the one used in Frostbite engine, and this here is used to render volumetric fog and light shafts. So this is also a unified system, meaning that the scene lights will interact with the fog, and this technique also heavily utilizes asynchronous compute. So let's move on to the actual algorithm. And so the first pass is voxelization. So here, local fog is generally contained within density volumes, which can be placed around the scene. And during this voxelization pass, the properties of these volumes are voxelized into a clip space aligned 3D texture known as a volumetric buffer, or V buffer. And the XY dimensions of this texture depend on the tile size, and it usually contains around 64 slices in Z. And this is followed by the lighting pass. So here they are approximately solving the volume rendering equation within each voxel using Monte Carlo integration. So then they accumulate the voxel transmittance along the camera array by ray marching. And next we have the temporal integration pass. So here, Monte Carlo integration generally requires more than one sample to be effective. However, here it is too expensive to take multiple samples within each voxel. So instead, they resort to using temporal integration, where they use reprojected samples from earlier frames to complete this integration. Now, this results in reduced banding, as you can see between these screenshots. Now let's go over a technique that's new to Unity, which is screen space deferred decals. So this technique has been used on many games shipped over the years, and it's quite easy to implement as it only involves rendering a box for each decal, and it integrates seamlessly with a deferred shading pipeline, letting you shade your scene and decals in one go. And you can also project decals on any surface regardless of complexity, because you don't need any custom UVs or subdivisions. Now let's go over the basic algorithm. So it starts off by rasterizing a box that represents the decal projective bounding volumes. Then in the pixel shader, they reconstruct the world space position at this point and project it into decal space. If it is beyond the normalized device coordinate range, you discard it. If not, it will be remapped to the UV range and sample the decal texture. Now, the properties of these decals are applied into a decal-specific G buffer called a D buffer or decal buffer. These can then be composited onto the G buffer. Now we'll go into our final section, which is post-processing. So here we'll be taking a look at a few of the interesting techniques such as ambient occlusion, motion blur, depth of field, and screen space reflections. Now let's start off with ambient occlusion. So this is based on the ground truth ambient occlusion technique shipped in many AAA titles, and the technique here is performed at half resolution, and the bulk of the time is spent on finding the horizon angle, which is the h theta angle seen in the diagram here, and p here is the position in the depth buffer, and r is the sampling radius. This technique utilizes spatial and temporal filters to improve performance and quality. Now, during the spatial gather pass, they consider samples from a 4x4 neighborhood with a single direction per pixel. And in the temporal gather, they alternate between 6 sample rotations for each frame and reuse samples from the 5 previous frames. This effectively gives us 96 combined samples for ambient occlusion. And here you can see the results after the spatial and temporal gather have been performed. Now let's talk a bit about motion blur. So their implementation here consists of 4 main passes, which are clamping motion vectors due to camera rotation, then finding the maximum velocity values per tile, then finding the maximum velocity in the neighborhood of the tile, and finally blurring the image in the direction of the motion vectors. Now, a little detail about the tile max pass. This is used to fix the sudden start of the blur. Using the tile max velocity gives you a much smoother gradient compared to the pixel velocity. Now, in terms of optimizations, the blur shader takes different paths for improving performance. If the tile max velocity is 0, no blur is required, so the shader takes the early exit path, which outputs the input pixel color. If the velocity is not 0, and the ratio between the min-max velocity is less than the threshold, then the fast path is preferred, which is a simple blur in the motion vector direction. Otherwise, it takes the normal path, which tries to recover the background and also prevent the background from bleeding onto the foreground. Now, they also use wave intrinsics or shader group vote in GLSL to prevent thread divergence when branching. Now, in this video, you can visualize the tile optimizations here. And as you can see, the normal path is only preferred for geometry edges. Now let's look at depth of field. So Unity uses a bokeh depth of field implementation. And the bokeh kernel here is generated in a compute shader and takes the lens properties such as the number of f-stops, blade count, etc. And this would determine the shape of the resulting bokeh effect. Now let's look at the actual depth of field implementation. So it starts off with a COC pass, which writes out the circle of confusion value for each pixel. Next, the near and far regions of the COC and color textures are separated. Next, the first 5 MIP levels of the far color and the far COC textures are generated. And then the near COC values are dilated to prevent them from bleeding into the far field. Then the max near COC and far COC values per tile are output into a buffer. Then the gather base bokeh is computed for the far field. Then it is combined with the scene color. Then the same bokeh is computed for the near field. And finally, the near and far field are composited together, giving us the final depth of field output. Now, this pass is optimized by executing the bokeh blur only on the tiles that actually require it. This is done by finding the tiles that actually require bokeh, then writing them into a tile data buffer, and then dispatching this compute workload indirectly. So if the max COC value is 0, then the tile is skipped. Otherwise, the tile's coordinates are written into the tile data buffer. Now, this greatly reduces the number of texture fetches that are required. Now we'll look at the final technique, which is screen space reflections. So this is a commonly used technique for getting dynamic reflections of on-screen objects. And this is also based on the implementation from Frostbite. So namely, hierarchical Z cone traced reflections and stochastic screen space reflections. So this consists of two main passes, the tracing pass and the reprojection pass. In the tracing pass, they compute a ray in the reflection direction for each pixel and march that until it intersects with the depth buffer. The areas that should receive SSR are masked out using the stencil buffer, and this ray is skipped if the surface is too rough, the normal points away from the camera, or if the ray points towards the camera. Finally, this pass outputs the ray hit positions into the render target. And in the next pass, which is our reprojection pass, they use the positions from the previous pass and reproject the color from the previous frame to use as the reflection color. This color texture has MIP levels which contain progressively blurred versions of the texture. So the MIP level for the reflection can be determined by the roughness value in the current hit position. So the main optimization used for this pass is a high Z depth buffer, which allows them to intersect the depth buffer much faster and quickly skip areas. And since it uses the color from the previous frame, the entire technique can be executed in asynchronous compute as soon as the G buffer has finished rendering. So hopefully this section would have given you a better idea of the post-processing implementations in this pipeline. Now we can move on to our final section, which is a brief look at the universal render pipeline compared to our HD pipeline. First off, the universal pipeline only features a single pass forward renderer, whereas the HD pipeline has a deferred renderer and a forward renderer. And the universal pipeline also supports a wide range of platforms, including OpenGL ES 2-level mobile devices, which leads us to have no support for compute, whereas the HD pipeline is mostly compute-driven. And it also has support for VR and basic PBR materials with metallic and roughness workflows. So nothing crazy like iridescence or anisotropy. And has some of the common AA methods, except for temporal anti-aliasing. And also, it uses a simplified variant of the post-processing stack from the built-in pipeline, which is more suited for mobile. So thank you very much.